Welcome to another exercise for the workbook Statistics, this time focusing on Loglinear regression. Our task here, it can be assumed that an exponential relation exists between the price y and the age x of a whiskey that can be modeled as follows. And we get here the model we should use. And well, the parameters a and b we should estimate using this data set for prices and age. Well, as I already said, use a suitable regression approach to determine the parameters a and b. Well, at this point, y, the price, is supposed to be the dependent variable and the age is the independent one. So how are we going to go about this? Well, first off, this is not linear, so we cannot use the classical approach for linear regressions. But we might be able to reformulate this in a slight way to actually make it work with the approach for linear regressions we already know. So how are we going to go about this? How do we linearize this function? Well, let's start with the original function. Then if we take a close look, the problem actually is we have a multiplication here and we take it to the power of something here. Both of these aspects can actually be made much simpler by just applying the logarithm on both sides of the equation. In particular, since I see this is the exponential function, that's e, the Euler number, I'm going to use the natural logarithm, ln. So if I apply this on both sides, I get ln of y, and on the right I get ln of a times e to the power bx. Since there is a multiplication here, I can draw the two parts apart. I get ln of a plus ln of e to the power bx. So this multiplication sign turns into plus sign if I pull the logarithm apart. I can only do this way, so only from multiplication inside the logarithm to the addition outside. Well, it's already a bit simpler. I already have like an intercept, but I still have this part. Here I can remember that the logarithm and the exponential function cancel each other out. So those two cancel each other out, leaving me simply with b times x. And that's pretty neat, because now I have a slope b, an intercept ln of a, and this is a line. That's a description of a line, which I can estimate using, for example, the least square method in the context of a linear regression. However, I need to keep one thing in mind. If I'm going to do this, I first have to logarithmize the y, because here as dependent variable, I'm going to use ln of y. So if I want to apply the method of least squares to the newly deduced regression function or regression model I earlier deduced, I first off copy the table from the original exercise text and I add one more column. In this column I'm going to calculate the mean of all the relevant variables. I'm going to do this for x as the independent variable, giving me here 14.8. I'm not going to do this for y because we are not using y directly. Instead, I'm going to append the table by 3 additional rows. And in the first row, I'm going to calculate the logarithmized values of y. So taking natural logarithm of 50, natural logarithm of 110, natural logarithm of 190, and so forth. And this row I'm going to average because this is the value I need later on. Also, that's what we already know from linear regression, I'm going to square all the x values, that's this additional row, and I'm going to average this row as well. And finally I'm going to calculate x times ln of y, so more or less independent variable times dependent variable, giving me this row with an average of 67.2027. And then I'm going to have these 4 means. And that's the 4 values I'm going to use in my estimation. Because if I'm starting with the slope parameter, with the parameter b, I can simply use the formula we know from linear regression. Instead of y, however, I have to write ln of y. So first off, I'm taking the average of x times ln of y, which is here the 67 point something, minus the average of x, so the 14.8, times average of ln y, the 3.5, so forth. So this part up here, that's already the covariance, and I'm going to divide it by the variance of x. The variance of x I can get with the average of x squared, which is here the second to last row, the 239.6, minus the average of x squared, so minus the 14.8 squared. I'm going to put all these numbers down here, enter them into the calculator, yielding me a result of 0.7422. So that's my slope, and the advantage is this is actually the slope as is, so I do not have to change this. I can directly copy this in my original model as well. That's a little bit different because now I'm going to get an intercept, but the original model doesn't really have an intercept. So here I have to do some recalculations afterwards. But first off, I can use for the intercept ln of a the same formula we might remember, which is just the average of the dependent variable, so the average of ln y, that's the 3.5, minus the slope, here b, from the last part, times the average of x, that's my 14.8. Going to plug in all the values and calculate the result, yielding me an intercept of minus 7.4749. However, this is ln of a, and for my model in general, I'm going to need the parameter a. So I first have to recalculate or solve this mini equation for a. Well, solving this for a, I can simply apply the exponential function on both sides, because exponential function and logarithm cancel each other out. If I'm going to do this, I have here a, here I have exponential function of minus 7 point something. This yields me the relatively small number of 0.000567. So the final model as such, just by combining this value for b, this value for a, giving me final model of y is equal to 0.000567 times e to the power of 0.7422 times x. That's the final model I've been looking for. Well, this then already concludes the session. I hope you enjoyed it. I say goodbye and see you next time.